So this is an important lecture on finite state machines, which is a topic that you should be familiar with from 3.11, but I think it's going to be useful for you to review because the notations, etc., the approaches that I use will look quite different from what you've seen in 3.11, I think. But before we get to state machines, I want to briefly review another concept that we saw in the lecture in the last video, essentially, which is kind of figuring out the critical path, or the length of a clock period for a given circuit. Okay, so here you have a circuit with 3 AND gates sort of in series connected to a flip-flop. And the question is, what is the best clock period for this computation? So gate delays are 1 nanosecond each, the setup time is 0.5 nanoseconds, and the hold time is 1.5 nanoseconds. So as usual, pause the video, solve the problem, and then check that you have the same solution as I do. So I think immediately you will say that the longest path in this circuit is basically from this input A to here, which should be 3 times 1 nanosecond. So it's 3 gate delays. If you paid attention in the last lecture, you would say that the clock period actually has to be longer. Namely, it should include both the critical path, which was 3 nanoseconds, but also the setup time. So the clock period should be longer than 3.5 nanoseconds, which is equal to critical path plus setup time. Remember that the hold time, which here is 1.5 nanoseconds, it does not really add to the critical path. It basically puts a constraint on the shortest path in the system, or the shortest path from one flip-flop to another in the system. So it basically says that the shortest path has to be longer than 1.5 nanoseconds. But in this particular system, all the inputs are, as it's drawn, all the inputs are external, and you don't really have a connection from another flip-flop back into the circuit. Good, but then maybe another thing that, as you look at this, another thing that you observed is that this is actually not a particularly smart implementation of this circuit. In fact, you could achieve the same logic with a better design, which would be to use the same number of gates, of AND gates, but order them a little bit differently. Namely, add A and B together here, add C and D together here, and the outputs, and then connect that to your flip-flop. So the clock period for this system should be larger than 2 nanoseconds plus 0.5, which obviously is much better than or 2.5 nanoseconds, which is obviously better than the 3.5 nanoseconds we had for the initial design. And this kind of really emphasizes sort of the importance of smart circuit design, in addition to hopefully also sort of reminding you of these concepts of hold time and setup time, which are, I think, concepts that circuit designers are generally familiar with, and it's useful for you to just remember what these time constants mean. Let's get to the main topic of this lecture, which is finite state machines. So what we want to do is we want to implement circuits that remember history, something like a traffic light controller, right? Where the traffic light, to know what to do next, it has to know what state it's currently in. So if the traffic light is green now, it will probably become orange later. And so you have to have a way of holding that state, or having information about the history. And in practice, in the circuit, this information will be held in flip-flops, of course, that we've introduced just in the previous couple lectures. But we'll see that sort of the design of sequential logic circuits, namely of systems that combine state holding elements with combinational logic, is a little bit more complicated. And in the next few slides, we'll sort of introduce these concepts of a state diagram, which can be used to describe the desired behavior. Introduce the concept of a state table, which is used to specify a function, sort of a little bit like a truth table. And we'll see how from the state table, we can then implement the combinational logic and also the state holding elements. And of course, this diagram at the bottom here just shows sort of an overview of what these systems are going to look like. So you have your combinational controller, there's external inputs, there's outputs. The external inputs in the traffic light case could be cars waiting at an intersection that trigger a sensor. The outputs, of course, here are the lights. And then there's some sort of some flip-flops that hold information about the current state, and of course the actual controller, which combines information, for example, from external inputs, like the fact that there is a car waiting, with the information coming from the history, namely, that there's a car waiting and the light is currently red, so let's switch it to green as soon as possible. Good. So on the left-hand side here, what you're looking at is a state diagram, and this is just kind of an introductory example that will teach us kind of all the basic concepts that are used in this to describe or reason about state machines and sequential circuits. So this particular state diagram corresponds to an odd parity checker. So it says you want to build a system that asserts the output, so it says an output is true whenever you have previously seen an odd number of ones. Not including the current one. Okay. So the concept is very simple. So in this particular case, these two circles here are the states. There's two states. I'm going to call this state 0 and 1. What I'm doing here is I've provided actually a state encoding. So each circle, as I said, is a state, has name. The two names are odd and even, corresponding to whether you've seen an even number of ones or an odd number of ones previously. The state encodings here will become useful in a second. These arrows between states correspond to transitions. The notation on the arrows is always of the form that you have an input first and an output later. And so every arrow needs to be labeled with both inputs and outputs. Typically, there is a reset, such that you can reset your state machine to a state of interest. Every possible transition sort of needs to be indicated. Sort of for every combination of, for every possible input and every possible state, the state machine needs to tell you what should happen. So for example, here you have one input and it can take only two values, so there have to be two arrows. Here in the case when you're in the even state and your input is a 0, well, after you've seen that input, you've still seen an even number of ones. So this arrow kind of says, okay, stay here if the input is 0 and produce an output that is 0. Conversely, if you're in the even state and the input is 1, well then you're moving to the odd state. But you're still outputting a 0 because the output corresponds to how many ones you've seen previously, right? And that was an even number. If you're in the odd state and you're seeing a 0, well then you're staying in the odd state, and since you've previously seen an odd number of ones, you're outputting 1. When you're in the odd state and you're seeing a 1, then you're moving to the even state and you're outputting a 1 because you've previously seen a 1. Okay, so I think this is a very intuitive representation, a description of how this particular system works. Now, from this state diagram, it's possible to write down a state table, and I've actually sort of walked you through this state table just right now. What the state table says essentially is on the left-hand side, it's very similar to a truth table. So on the left-hand side, you have the present state, which in this case can be 0 or 1, and the input. And on the right-hand side, you basically just write down what happens in each of these cases. So again, we said if the present state is 0, even, and the input is 0, so that was this arrow, then your output is 0, and your next state is even or 0. If your present state is 0 and input is 1, then you're going to the odd state and you're outputting 0. If you're in the odd state and your input is 0, then the output is 1, 0, sorry, 1 and 1. And here 1 and 0. Okay. So once you have this state table, you can essentially think of it exactly as you would think of a truth table. So you can just, what you're trying to do is you're trying to build a relationship between the right-hand side of this table and the left-hand side. And so in this particular case, you can essentially see what this relationship is. I mean, you can just look the output and you see that it's essentially the same as present state. So you can write output out is present state. And you can probably also see that next state here is essentially the XOR of present state and in. So, oops. Next state is present state XOR in. Okay? So that's essentially, now that you have this, you can go and actually design your circuit. Okay, so this is what the circuit is going to look like at the top here. So these are the two relationships we just derived. Here, of course, you see the XOR gate calculating next state. Output is just present state, as shown here. Because you only have two states, and then correspondingly they can be encoded by the values 0 and 1, you just need to have a single flip-flop, because the flip-flop can be in one of two states. So that's relatively intuitive. Of course, the flip-flop as an input, it takes kind of the next state, so the output of the combinational circuit, and then it holds on its output the value of present state, which serves as the input to the combinational circuit. Good. So the diagram here at the bottom is just sort of trying to make it intuitive how to think of these circuits that are sort of now sequential, right? And so we have to go essentially clock period by clock period. So I'm just going to look, assuming that my flip-flop is positive edge triggered. So interesting things will happen only at the positive edge of a clock. Just indicating this here for convenience. Okay. So now, what this tells me here is that the input starts at 1, present state, output starts at 0. What I can do is I can calculate during the given clock period, I can calculate, for example, what next state is, which is XOR of input and present state, which in this case is 1, right? And this next state value will be held here at the D terminal of the flip-flop. And at the edge of the clock, next state becomes present state, right? So the value that I've calculated at this clock period becomes the value of present state at the next clock period. And then I can repeat this exercise. And so now, present state is 1. But the input value here, somewhat before the clock edge stopped to 0. So again, I calculate the XOR of 1 and 0, which will remain 1, and so the next state, which was 1, becomes present state again in the next clock period. Here again, input is 0, this is high, so XOR remains 1, so this remains 1 another clock period. Here now both of them are high, so input and present state are high. 1 XOR 1 is 0, so at the next clock period I go down, this goes back up, so it remains high, goes back down, so 0 XOR 0 remains low, 1 XOR 0 goes back up, 1 XOR 1 is low, high, and we're here. Okay, so hopefully this is clear. So essentially you're calculating next step values for a given clock period, and then at the clock edge you're updating present state by reading in the next state from the previous time period, and you're recomputing. Okay, so now to just introduce this a bit more formally, let's first talk about state diagrams. So state diagrams are sort of a graphical diagram or graphical representation of the finite state machine behavior. As I already said, states are represented by circles, transitions are represented by arrows connecting states, and then labels on transitions are given in the format of triggering input pattern / outputs. And obviously, you know, in this particular case there was just one input, one output, but you could have much more complicated patterns of inputs. I should also say that here we're covering mealy machines. More machines are a different representation of state machines, where the outputs, instead of being associated with the inputs, are associated with states. So you would write the output pattern onto the state. In some ways that's more intuitive, but it turns out that in practice people use mealy machines because they tend to be more compact, and it's obviously always desirable to kind of make systems or sequential circuits that are as compact as possible. So going forward, a lot of what you're going to do in this class is essentially design various types of finite state machines. And this can be broken down in a few steps, and really only the first step here is hard, namely kind of understanding the problem, right? If I ask you to design a traffic light controller, you have to kind of figure out how to translate that request of build something that determines how the lights should switch to a state diagram. Once you have the state diagram, you can draw that. That's relatively straightforward, and everything becomes very automated. Like from the state diagram you can derive a state table. It's completely automated. You just read off states and the values you've written on the arrows. From the state table you can use everything you know about Boolean minimization to derive sort of a minimal combinational logic circuit, and then you can just actually build the sequential logic device.